So welcome back, and in continuation of the two combinations, parallel and series combinations, or series and parallel combinations, we will talk about the mixed combination today of capacitors and relate it to the case of the springs, the resistor, the impedance, etc. Okay. Sure. Now I am taking, you see, and mind it, all the capacitors that we have here, they will have one plate positive, another plate negative, equal charge and opposite charge on each of them. The charge resides on the inner sides, not on the outer sides. This has to be borne in mind. So, let us see that here is a structure and here is the equivalent. So, I have 4 capacitors over here, C1, C2, C3 and C4 between the points A and B. Okay. Now we can subject it to a potential difference which I can obtain, and I can vary also, doesn't matter, with the help of a cell or a battery of cells, whatever, doesn't matter. You will understand that slowly and gradually. And in the equivalent, we also again have the same application of the potential difference from the battery or from the cell. Okay. Now be attentive. You have to be very attentive because I am not dealing in numbers. I am dealing in algebraic symbols. Algebra. Okay. Algebra came in the 9th century, and that was given and perfected by a scientist of Iranian origin. His name was Muhammad bin Musa Al-Khwarizmi. He was from the town of Khwarizm, and he worked at the Darul Hikmah of Baghdad, a big institute for the scientists, for the engineers in those days, in the what you can call as one of the famous universities in those times. Muhammad bin Musa Al-Khwarizmi, he talked in terms of symbols. And ladies and gentlemen, boys and girls, you must have heard a word, algorithm. This word algorithm, which defines how to solve a problem, the way how to solve a problem, how to draw a flow diagram in computers, that also honors Muhammad bin Musa Al-Khwarizmi. You can always substitute values for C1, C2, C3, C4. Okay. Now before I indulge in obtaining the value of the capacitance between the points A and B, because of the combination of these capacitors, let me tell you about this symbol. If I have a line like this and I put plus here and minus here and write a V over here, this means that there is a drop of potential from positive to negative. And this drop is also known as fall of potential. Otherwise, if I have a symbol like this, negative to positive, the arrow goes like that, then of course we understand that this is a rise of potential. So this is one of the symbols that we use, that I've used over here for a drop of potential from the point A to B, and also over here for the drop of potential point A to B. We don't have anything, we don't write like this. Will not write like this. This is it. Okay? That's not our cup of tea. Okay. Now let's see. C1, C2, C3, C4. Okay. And let's see the data, associated data. And of course C, which is the equivalent capacity. So there I write in these compartments the values related with C1, C2, C3 and C4. Oh, sorry, I should have written C4 also. Okay, so I should have written C4, Q4 and V4. Okay, like that. Doesn't matter. So this is in keeping with what our great grand old father, the father of algebra, he could have done. Okay. Now this is one thing. So this is the set of data associated with C1, C2, C3, C4 and C. No problem. It's easy. Now let's see what it means VAB. So I will subscribe to VAB as equal to VA minus VB. This is always different from like delta V or delta X. Delta X means the value after minus the value before. But here it is the value first and value later. Okay. So this is signifying a drop or fall or negative rise. Okay. Because drop is a negative rise and rise is a negative drop. Try to understand that. Must be clear about it. Okay. Now to solve this, and before I arrive at that, let's take what we have learned in the case of the series combination of two capacitors. Okay. In the series combination of two capacitors C1 and C2, we have potential drops V1 and V2. And the equivalent over here, QCV, so V is equal to V1 plus V2. But the first plate that we encounter over here, inside of it plus Q, inside of this one minus Q, inside of this plus Q, inside of this minus Q. So in that series combination, two capacitors are any number, the charge will remain same. Okay. Okay, friends. But the potential difference and the potential difference will add up to give the total potential difference. So this is why. If the value of C1 is equal to the value of C2 is equal to C0, then the net capacitance, you can see, will become equal to C0 by 2. That means the net capacitance, the equivalent capacitance will get halved. If there are 5 of them, then C0 by 5. N of them, C0 by 8. Okay, no problem. Then the second thing that we have learned is the parallel combination of two capacitors. Okay, between these 2 points, the extensions have been shown. This is C1 and this is C2. Look here. what will happen is that whatever is the potential difference over here will be the potential difference across the parallel path, and the total charge will be divided between these 2, these 3, these 5, these n capacitors in parallel. So I can write Q will be equal to Q1 plus Q2 plus and so on, Qn, etc. And in this case, like we have, if the capacitance equal to C0 and C0, then what we'll get? I'll get 2 C0, okay, because C is equal to C1 plus C2 plus C3 and so on. One more thing, very interesting, that if we have these two capacitors like capacitors of the same capacitance value C0, and let us consider the separation between the two of them is a constant d, then what basically happens is that this area over here of the plate becomes doubled. So epsilon naught A over D, the value of the capacitance, epsilon naught A upon D. A doubles, so the capacitance doubles. And here in this case, you can see if they are similar, the D value is the same in both the cases, A value is also the same, okay. Then what happens is A does not change and the D value becomes double, basically. Because this, look at this edge, this is all metal. So all these metallic points, okay, they must have the same potential, okay, and therefore I can say, I can even remove that part, bring it here, remove that, and the D value will double. So when the D value doubles, look here, epsilon naught A upon D, D doubles, so the value becomes equal to C naught by 2. Okay. So there is now more clarity for the series and the parallel combinations. Okay, friends. Now, more often than not, if you just have a look at this kind of structure that I have shown over here, then suddenly it comes to your mind, to the bhola bhala people like you, okay, simpletons like you, that C1, C2 and C3 they are in series and this C4 is in parallel. No sir, no sir, no ma'am, not at all. Why? Because what we have to do is, we have to travel, we have to move from A to B. And let's see what is there. From A I come to small a, and we encounter with the capacitor C1 having the data C1, Q1, V1. No problem. Then from the point A I want to go to the point B. Look here. What happens is, I have one path to go like this, where we encounter C2, and there is another parallel path where I encounter C4. So these two paths from A to B like this and A to B like this, they are the parallel paths. They are just like over here. So these two are in parallel. These two are in parallel. So the value will be equal to how much? C2 plus C4. Very simple. Now we have three parts in series. One is this one, another is this, and the third one is this. They are all in series. Okay. So suppose I calculate the value C1 plus C4. So the net value for that C will become equal to how much? 1 upon C1 plus 1 upon C2 plus C4 and plus 1 upon C3. Okay, and then work that out, calculate these fractions, reverse the value of C, and you obtain the result. So this is the simple method that you do it. Look here, there is another thing. This is the combination series. Can I put C2 here and C1 here? The answer is yes. No problem. So, while doing problems like that, where the values are given to us, maybe sometimes not in numbers, but otherwise C2, C3, C4, C, like any kind of value. What is there? What is there? That I can bring this C3, look here very intently, from here I can shift here. So first C1, then C3, then C2 plus and C4 combination. Or I can put it here. Or I can put it here because they are in series, this combination. Okay. So this is a commutating property. We can commute them from here to there. Like I said to you that in the case of the vector A dot B, the vector A dot B is dot product of the two vectors A and B is equal to B dot A. So what I do? I just change them. But not in the case of the cross product. Never. Because in the case of cross product, A cross B is equal to minus B cross A. Okay? Anyway, I should not go astray. So friends, in solving any kind of the problems like that, we have to travel from the point A to point B, whatever way. We can have a topology like this, we can put it here, we can put it here, no problem. Okay, check that. You will be simply successful. And look here, what is needed to solve such problems is a single formula. Q is equal to CV. So C is equal to Q upon V, or V is equal to Q upon C. In a matter of a split of a second, you should be able to write from Q is equal to CV to V is equal to Q upon C. When I say split of a second, I mean split of a second if you are an average student. If you are brilliant, then you can write it in few tenths of microseconds. Okay. I am going to compare the things. You know that V is equal to Ri from class 9th, or you may have been told in your classes, and this is basically our friend Ohm's law. Ohm's law. Okay, Ohm's. V is equal to Ri. And this Q is like this. I get V is equal to Ri, V, I, and we get. Okay, similarly, F is equal to Kx. So this is the case of resistors. We'll talk about the resistor combinations. I have talked to you about the spring combinations. F is equal to Kx. And later on, we can talk about, when we talk about the alternating current systems, then V is equal to Zi, where Z is the impedance, Z is equal to R plus Jx, and Z square is equal to R square plus X square, J is equal to under root minus 1, which is just like the iota of complex algebra. Okay. we can do similar kind of things. No difficulty, no problem, no nothing, not at all. The only thing is, you need to visit all these questions regarding the combination of capacitors, etc. 2 hours. And capacitors per resistors, total 3 hours. Okay? Capacitor plus resistors and also the springs, 3.5 hours. And your masters. And inductors and this and that. 5 hours, the whole thing is finished because the mathematics is the same. Okay. Now what can I do is that once I am able to calculate, here V, here C, I can calculate the value of Q. The value of Q will be same over here and here, but here it will be split. Okay, Q2 and Q4. Okay, you can calculate the value of Q1, Q2, Q3, Q4, etc. Also you can calculate the value of V1, V2, V3, V4, etc. And this, don't do it algebraically initially. Do it with the help of the values that are given in your help books, textbooks, or what you do for the books where you have questions from your competitive examinations. The medical students who want to go for the medical stream, they must visit such chapters in the engineering ones also, and the engineering students must visit otherwise. Okay. Now I am going to tell you a combination of capacitors which was proposed by Mr. Wheatstone, the Chakki wala. Okay, Chakki stone. Okay, just fun. I'm being funny, just kidding. There is nothing like that. Wheatstone is Wheatstone, and bridge is the same bridge going across. Okay, so there are two ends to it. I have a capacitor C0, and this capacitor is NC0. This capacitor is C star, and this capacitor is NC star. Okay, and what we find is that this upon this is equal to this upon this, this upon this is equal to this upon this. Okay, right? So this is called, in such a situation, if this kind of a ratio exists, and similarly I can have R0, NR0, okay, R star, NR star for resistances, and for C dash that I am putting between these two, I can have R dash. Okay. Now I'll do it. After I tell you the Wheatstone bridge in the case of resistors, I'll explain to you what will happen in the case of capacitors also. Okay, friends? And this and that. We can take this also. The impedance. And this X is reactance. Okay, I'll talk about that shortly, not very far off, maybe 10 lectures away from now. So what we find is a very interesting feature. The very interesting feature is that if such a combination exists, all I have to do is to show that the potential difference between these 2 points is equal to 0, 0 and 0. So when the potential difference is 0, V is equal to 0, Q will be equal to 0, C will be there. Okay. So I can have any value of C, it doesn't matter, from 0 to infinity. Okay. So what we do in a Wheatstone bridge system is that we just remove this from here. Okay. So the A value becomes very, very large. Okay. And so that we can say the capacitance between the two of them has become sort of infinite to 0, any value is possible. The whole thing is that the potential at this point, the potential at this point should be equal to 0. So friends, I have done the mixed case with the help of the case of series and the case of parallel combination of capacitors. And I have told you how all these values can be calculated if the value of V is given to us, should be known to us, it should be known to us. And one thing is there, that these capacitors individually or in any combination, they are not going to obtain this set of values immediately. Okay. It will take some time. It will take some time before they settle to the steady state. In that time, in that small time, there is always a current through all these capacitors in any combination. Even in this simple case, there is a current which is flowing. But the moment the value of, suppose I charge with the help of a battery, when the EMF of the battery, electromotive force, which is a misnomer, okay, the battery voltage becomes equal to the voltage over here, then there cannot be any further flow of current. Okay. So a static condition is obtained, an electrostatic condition is obtained. So you have to bear in mind that there is something which happens before the charging takes place. So charging and discharging of capacitors, it will take a lecture later on, okay, when we teach to you the steady state voltage applied to a combination of a capacitor and a resistor. Now, very interesting thing, a very interesting thing. Suppose I have a capacitor. I put it to the battery, V volts across it. Okay. Now I have a similar capacitor. I take the battery off. Okay. And I have a similar capacitor. This side positive and this side negative. I put it positive to positive and negative to negative. So naturally, now it cannot have all the charge all by itself. The nature says that please share. And if the charges are shared, that very interesting thing that you obtain, and we'll see, because I'm not doing that because the energy of the system I have not told you about. So the next item that I'm going to discuss with you is the energy stored in a capacitor. The energy stored which can be later on used for useful purposes. So thank you very much for the day. Okay, I'll do that in the next lecture.